All right. Hi, everyone. Welcome in. Today, we have a continuation of our thematic series on distribution shift, and we have a talk by Victor Veitch from University of Chicago on linear structure of high-level concepts in text-controlled generative models and the role of causality. Today, our discussant will be Francesco Locatello from Institute of Science and Technology, Austria, and I hope you all enjoyed the talk and the discussion. If you have questions, please submit them through the Q&A. I'll switch to Sarah, who will kind of explain a little bit more about how that works.
Okay, thank you very much. So if you have clarifying questions, I will ask them during the talk of Victor. And if you have longer questions, we'll ask them after the discussion. And yeah, please do not submit them on the chat, submit them on the Q&A. Thank you very much.
It's kind of all. All right, Victor, feel free to start sharing.
Great. Okay, so the Chrome tab is visible now?
Yes. Well,
perfect. Good. Fantastic. Okay, good. So hi, thanks very much for the invitation. I'm going to talk about linear representations in generative artificial intelligence. This work is going to cover a mixture, or this talk is going to cover a mixture of work from two papers. It's going to mostly be about the second one, linear representation hypothesis in the geometry of large language models. But also we'll mix in some ideas kind of like unattributed from this concept algebra paper that we wrote previously. And I'll just say Zahal, Lin, and Kyo are students of mine at the University of Chicago. YG is a postdoc with me, and Jeff is now a faculty at the University of Waterloo. And they're all fantastic. Definitely talk to them if ever you meet them at a conference or whatever. Okay, so this is going to be a slightly odd talk because it's a thematic series on distribution shift, and the talk is not really about distribution shift. And so here is my one-slide summary of why I'm doing this thing. So part of the question here is, part of the landscape of machine learning right now, right, is that we seem to have switched to these like truly enormous models trained on very, very large data, right? Maybe that's not everything, but it's at least a thing to be very interested in. And it's a little bit unclear, like how, like semi-classical issues in supervised learning, things like distribution shift, actually come up as like relevant for these things, right? Or spurious correlations or whatever, right? And so I started down a path thinking a lot about that. And what we're going to talk about here is where I ended up. And the start and the ending maybe don't feel that closely related, but hopefully it all makes sense by the end of the talk. Okay, so the very first observation, like the sort of key interesting point about these generative AI systems, and here I mean mostly large language models, is that everything that is interesting about these systems, the behavior that we actually care about, is emergent, right? And by emergent, I mean we train on some kind of proxy objective, which is not the actually thing. This is not the thing we actually care about, right? So like typically we're just predicting the next word, right? And then we test on things like high level understanding, right? So like, can I translate French accurately? Can I solve math problems? Do I write code that compiles? Things like this, right? And so the point is like the behavior that we care about is not really behavior that we designed into the system. It's stuff that just like popped in, right? And this is, I think, quite different even than the supervised learning setting, right? And it really creates some like fundamental questions, right? So a first one is like, well, what are the limitations of these models, the fundamental limitations of these models, right? So in particular, if we just like make bigger and bigger decoder-only LLMs and we ingest all of the text on the internet, does that give us like genuine artificial intelligence? Does that give us like superhuman intelligence, right? Like I think it's actually very difficult to give a confident answer to that question right now, right? Another question which is closely related, which is, we now have these like enormous black box systems. We want to use them to do things like make substantive decisions in the real world. When can we actually trust them, right? So by that, I mean both like, when are they competent and also like when are they honest or reliable? Okay. And so I think these are like the core issues, like the things that really matter in this generative AI space, right? And at least my response to this is to say, well, the thing that we would really like to do at this point is develop some kind of like science of generative AI, right? So this is distinct from trying to engineer better systems, right? What we want to do is take these systems which occur and then try to really understand, the root causes of their behavior, like what is actually going on here, right? So this is the highest level goal. Okay, so let me zoom in. So this talk is going to be a bit a particular subroutine, like one step up the mountain towards that goal. So we're going to be looking at the so-called linear representation hypothesis. Okay, so context for this, the way these systems all of these generative AI systems, is that we take some input text X, a prompt, and then map it to some kind of representation that lives in a vector space. Okay, and then we also have some sampling procedure where we generate some kind of output Y sampled from a distribution that is defined by this representation vector, right? So in large language models, that output Y, right, is just a word from a vocabulary. In text-to-image models, that output Y is some like natural image. Okay, and the goal that we're going to look at here, so refining a little bit, is to try to understand how semantic structure, so like things like meaning, are encoded in the algebraic structure of the representation vectors, right? And so by semantic structure, I mean questions like, say, in the context of LLMs, is the output in English or French, or is it in past tense or present tense, right? In the context of text images, I mean, is this a photograph or a painting? Is this a picture of a dog or an astronaut, right? So variables that would be semantically meaningful to humans, right? How do those get encoded in algebraic structure? And the specific thing that we're going to be looking at is this bit of, let's call it folk wisdom, right? So this is not a thing that we came up with. It's a thing that exists in the zeitgeist. The so-called linear representation hypothesis, which I'm going to summarize as the idea that high-level concepts are encoded linearly in the representation space, right? And I'll say in a minute more precisely what that conjecture means, right? But this is like at least a widely believed bit of folk wisdom, right? And the key point here is like the linearity is some kind of non-trivial prediction. Okay, and so within this, within the linear representation hypothesis, we're going to be interested today in three particular problems. So the first one is, what does linear even mean, right? So I said this folk wisdom exists, but if you try and really dig into like make that statement precise, it's not so clear. The second one is that when we look at these linear representations, so say we have a linear representation of the concept of like English versus French or man versus woman, right? Like a thing that we want to do with them is say interpret models by measuring cosine similarities between vectors, right? Or modify models by, say, projecting out certain subspaces and whatever, like this flavor of thing, right? But so it's like if we have linear structure, the reason that we care is that we want to do linear algebraic operations. Okay, but the key thing is that if we're doing some kind of linear algebraic operation, we need an inner product on a vector space, right? And it's really unclear why like the Euclidean inner product on a representation space would have anything to do with like high-level semantics understood by humans, right? So what's going on with that? Okay, and then the third question is, well, if this linear structure is real and well-defined, where does it come from in the first place, right? So is this something like idiosyncratic to the structure of language models, or does it have some kind of like different origin, right? So these are the three questions we're going to be interested in today. Okay, so we're going to start off talking about this paper with Kehoe and YJ. Okay, so the first question is, what does linear even mean? So there are at least three things that people have meant by this in the literature. So the first one is what we're going to call a subspace notion of linear representation. So this dates back to like these very famous word-to-vec examples, right? Where the idea here is that if we take pairs of words, right, or like counterfactual pairs that differ only on a single concept. So here the concept is sex, right? Then every such pair that differs only on that concept should be parallel, right? So this is the famous result that like king minus queen is approximately parallel to man minus woman, right? Or more precisely, the representation of king minus the representation of queen is parallel to the representation of man minus the representation of woman, right? So the first notion that people have studied is this, all pairs that differ on a common concept live in a common subspace, right? A common one-dimensional subspace. And so then we take that one-dimensional subspace to be the linear representation of the concept. Okay, the second notion that people have studied quite a bit is this so-called linear probe notion. So the idea here is that you have some input text, right, which generates some output, and then you label your output by high-level semantic properties that you might care about, right? So high-level semantic properties are things like, is this in English or is this in French? Or is this about a man or is this about a woman, right? And then you train a probe to predict that high-level semantic property, right? And by training a probe, I mean you run logistic regression on the activations of the internal representations of the network. And the really key point here is that logistic regression, so a straight logit linear model, very often works well, right? And so this is surprising, right? So it's obvious that in the internal representation, right, information about what the output language is encoded, right? So it wouldn't be surprising to say, oh, I could train like a deep neural network to probe for this concept and like accurately predict it, right? The surprising observation is that you don't need any nonlinear structure. It just like straight logistic regression tends to work, right? So this is a second thing that people have observed and like put under the bucket of linear representation hypothesis. The third thing is this intervention notion, right? Which basically says, well, suppose that we take the representation of some sentence. So here the prompt is he is the whatever, and it outputs the next word is king. Say the next most likely word is king, right? What we find sometimes is that it is possible to find a vector encoding the male to female concept, where if we just add this vector onto the representation here, right, we will change the concept represented by this vector, right, in isolation, right? So we will change the next most probable word from king to queen, right? And so the point is like there, three notions of representation: one about subspaces, one about linear probing, one about intervening on the concept. Okay, and all three of these things, have sort of been studied in various combinations empirically in the literature. There is sort of like an aggregate body of evidence that sort of suggests overall there is something like this structure going on. Okay, so the problem that we have here in terms of what does linear even mean is that these three notions are not obviously the same notion, right? And so in particular, it's not clear how these three notions relate to each other, nor which might be the right notion of linear, right? And so, like we might imagine, actually we have three separate linear representation hypotheses according to these three notions, or like, it's unclear how we might reconcile these ideas. Right, okay, so we're going to zoom in and focus on this question. How do we reconcile? Okay, and so the basic strategy here is going to first be to use the language of causality to define what a high-level semantic concept is. Right, so we need a formalization in order to get anywhere, and our formalization is going to be a causal one. The second step is going to be to use our now formal notion of concept to define the subspace notion. So this like king minus queen parallel to man minus woman notion. So we're going to give a formal definition of that. And now once we have that formalization, what we're going to do is prove some theorems that connect the subspace notion to the measurement and intervention notions. Okay, so this is the basic game plan. Okay, so before we do that, we need just a tiny bit of background on large language models, so to establish some notation, right? So as a black box, right, the way that we view these models is we take in some context string, like he is the, which we're going to call x here, right? And then the model defines a distribution over some fixed vocabulary of words, right? And so it's going to sample from that distribution one by one, right? And so the next word, the completion of the sentence might be king, to get he is the king, or man, he is the man, or he is the PhD, or whatever, right? So there's some distribution over next possible words. Say in llama, which is what the experiments will be on, there's a fixed set of 32,000 vocabulary terms here, right? And of course, this is as rich as English expressiveness. Okay, and now the particular way that this distribution is defined is the large language model, right? So that, by which I mean stacks of decoder-only transformer blocks, right? Is going to map the input string x to a vector in some d-dimensional vector space, right? So it's a mapping from free-form text to a d-dimensional vector space. Similarly, we're going to associate each word in the vocabulary with some unique vector in this d-dimensional vector space, right? Okay, and as to establish notation, we're going to call the representations of the words unembedding representations, right? And the representations of sentences produced by the language model embedding representations. Okay, and so when you train a large language model, the thing that you are doing ultimately is learning to produce these embedding representations and learning to produce these unembedding representations. Okay, and once you have them, you define a vocabulary, you define a probability distribution over the next word according to the softmax distribution in the usual way, right? So this is like the really standard component. Okay, so I'll just comment. One thing is like, you know, nothing in this talk is going to rely on like details of like the transformer architecture, right? This is really just about the structure of like probability distributions defined via softmax. Okay, so this is all the background we're going to need.
Sorry, Victor, we have already one question in the Q&A. I'm going to ask you. It's from Taha Bahadori, and the question is: the LLMs usually learn representations that are context dependent. The representations differ from a context to another one. How can we state the linearity given the variability of the representations given the context?
Yeah, sure. So the context here is the sentence, right? And so indeed the representation is context dependent. It's a representation of the context string, right? And so I mean we will see precise statements of the linear representation hypothesis in just a moment. So hopefully that answers the question. We'll push on. But yeah, that's a great question. Okay, good. So this is the background. This is all we need. Okay, great. So the first step was give a notion of what concept means, right? So if we're going to say anything about linear representations of concepts, we need to say what a concept is, right? And so the idea that we're going to use here is to view the generative process of the large language model as taking in some context string, right? And then defining via this context string a probability distribution over latent variables, right? And now from those latent variables, generating the output, right? And these latent variables are the things that we're going to take to be concepts, right? So here, this latent variable W is the male to female concept, right? This latent variable Z is an English to French concept, right? And now fundamentally, these are human defined things, right? They need not have any like ontological status in the language model, right? But the point is there is some latent variable space that we can reason over, right? And in particular, the property that we need from these latent variables is that it is a well-defined operation to intervene on them, right? So we can intervene on this W latent variable, right, which might have been set to female to make it male, right? We can intervene on this like English latent variable to make it a French latent variable, right? And now depending on the setting of these latent variables, right, we get different outputs, right? So if we say had English male, maybe the next word is king, but if we had French female, the next word would be rien. Okay, and so the model here is just like we have some latent variable space and we imagine we can intervene on the latent variables, and things that we can meaningfully intervene on, right, where it's well-defined to intervene on, are the things that define our concepts. Okay, so we're actually going to specialize just a little bit further, right, and say actually for binary concepts, we're going to define them via pairs of counterfactual outputs, right? So if I can give you a pair of random variables that are counterfactual, varying just in one thing, then the thing that they vary in defines the concept, right? Okay, so to make that concrete, if I want to define this concept of male to female, right, I'm going to give you the following set of pairs. So this counterfactual random variable is a random choice from man, woman, king, queen, uncle, aunt, and so forth, right? So just a bunch of pairs that differ exactly on this one concept. Okay, so now we have a workable mathematization of the notion of high-level semantic concept. Okay, we're actually going to need one additional notion here. So we say that a pair of random variables, or sorry, a pair of concepts, such as male to female and English to French, are causally separable if the counterfactuals are well defined for all possible combinations of the values, right? And so the intuition that this is capturing is that I can freely vary, is the output about a man or a woman, and I can freely vary is the output in English or French, right? So we're formalizing that notion of these are things that I can vary freely of each other. Okay, good. So the next step, now that we have these notions, is to try to give a formal definition of the subspace notion of linear representation. Okay, and so the very first observation here is that there are actually two representation spaces at work, right? So there's the embedding representation, so the representations produced by the large language model, in the forward pass, and there's the unembedding representation, which is the representation that exists in the space of the word unembedding vectors, right? So the point is there are two vector spaces at work here, right? And so it is natural to ask for representations in both vector spaces, right? So we want to define both of those things. Okay, so the unembedding representation of a concept turns out to be a lot easier to define, right? At least in this setup. So what we're going to do is say that a concept W has unembedding representation gamma bar W if for any counterfactual pair differing only in that concept, the difference in representations is parallel to this vector gamma bar W, right? And so this is just the idea that king minus queen, right, is parallel to gamma bar male to female, right? And also man minus woman is parallel to the same vector, right? So all of these things are parallel to a vector. We call that direction the unembedding representation. Okay, we also need a notion in the embedding representation space. Again, the idea is going to be to say that all counterfactual pairs should be parallel to a direction, right? So we say that we have a linear representation in the embedding space if all counterfactual pairs of prompts are parallel to that thing. Intuitively, what that means is that if we look at the difference of sentences like he is the and she is the, right, then these only differ in the concept of male versus female, right? And so there should just be if we have a male versus female direction, there should just be a single fixed direction that all such pairs of sentences are parallel to. Okay, now I put counterfactual in scare quotes. This is one of those slides where it creates a lot of confusion, which is why we have the intuitive one. Plug your ears if this will create excessive confusion. So I gave you a formal definition of what the unembedding representation was. I dodged giving you a formal definition of the embedding representation. So here it is, because I feel a compulsion to do it, right? So what does it mean to have a counterfactual pair of sentences, right? Well, or counterfactual pair of prompts, right? Well, we're going to view the prompts as defining probability distributions over these concept variables, right? And we say a pair of prompts is a counterfactual pair if the probability distribution over the concept's target is different between those two things, but the probability distribution over every causally separable target is unchanged between the two, right? So that's saying, he is the and she is the. They have different probability distributions over whether the output will be about a man or a woman, but they have the same probability distribution over whether the output will be about English or French. Okay, but the only takeaway that I want from this slide really is it is, once you have this language, you've set up this latent variable model and interventional notion of concept, it's fairly straightforward to give a formalization of what concept means in a way that you could, mathematize. Okay, so then the first result of this paper, the first pair of results of this paper, right, are connections between the subspace notion, so there's two of them now, and these measurement and intervention notions. And so the first theorem is that if you have an unembedding representation vector, so if such a representation exists, right, in the subspace notion, right, then that representation vector will act as a logit linear probe for the same concept, right? And so what that tells you is that if like the subspace representation in the unembedding space exists, it must also be the case that the linear probe notion exists and is the same representation direction, right? And this result follows fairly immediately just from like the definition of the subspace notion and the structure of softmax probability distributions. Okay, so we've now achieved a partial unification, right, between unembedding subspace representations and the representations learned from like linear probing. Okay, the second result, right, which is analogous to this, right, is that if an embedding representation exists, right, so all counterfactual pairs of sentences live in a common subspace, right, then what happens is that embedding subspace representation vector will always act as an intervention representation, right, which means I can take sentences of the form like he is the minus she is the, right, construct that difference of vectors. I can now take a new sentence, right, which is about a man or a woman, and then shift the output in isolation, right, by adding on this difference of concepts, right? Okay, so that's like a highly non-obvious statement. This one's like a little bit more involved, right? But the punchline, is that if you have this embedding subspace notion, you will immediately get the intervention notion for free, right? And so in particular, this also tells you you can construct linear probes via counterfactual pairs of words, and you can construct intervention vectors via counterfactual pairs of sentences. Okay, so first two results, we have achieved a partial unification. Okay, so let me just pause and review the story so far. Right, so the issue that we have is that there are three apparently distinct notions of linearity: the subspace, measurement, and intervention notion. What we did was try to formalize this subspace notion using causal language, right, which led us actually to two distinct kinds of representation, an embedding representation and the unembedding representation, right? And then using that structure, using that formalization, what we can prove is that the unembedding representation acts as a measurement representation, and the embedding representation acts as the intervention representation. Sorry, let me take a pause because I see chatter in the chat. So I'm not sure why the slides did not go to Dominic, but the version I sent Francesco yesterday is basically up to date. And so if you can use that, that's fine. Sorry, this is a detour for those not seeing the panelists chat. Okay, but so this is the story so far. Okay, so
we also have, maybe before you continue, I wanted to maybe check. So there were some questions, and I assumed that maybe these questions would be answered a bit later on. But I think one of the questions was in the example you had, the context was in English. Mm-hmm. And so when you are trying to check how it was in French, this was a bit confusing. So this was let's say, the comment from one of the people in the audience. Do you want to comment on that a bit more?
Yeah, so yeah, okay, so let's go back to these notions, right? So okay, so the claim here is that if you have a linear representation, there is a single fixed direction in each representation space that works for all pairs of words, right? And for modifying all sentences, right? So for the subspace notion, right, we would say the English versus French thing might be Roy minus King, Rien minus Queen, right? So like the counterfactual pairs of words would be French words and their English translations, right? Mm-hmm. For measurement, the claim is that we could predict the output language, right, using a single fixed linear vector, or we can predict whether the output is about a man or a woman using a single fixed linear vector, and that works for all possible input sentences, right? So of course, if the input sentence is either in English or in French, very likely the output is in English or in French, right? But you could say something like, you know, dear GPT-4, pick your favorite language, and then write me a sonnet in that, right? And the claim here is, you know, we'll be able to predict the output language from the representation using a single fixed direction. Okay, and in the case of the intervention thing, the claim is that if we start with a sentence like he is the, right, there exists some vector, right, in the embedding space, such that if we add on that vector to the representation of the sentence he is the, right, the output will now be in French instead of in English, right? So we can change the output language in isolation by adding on some suitable representation vector, right? So, and so this is true for like all concepts, right? So it's like the subspace notion, the measurement notion, and the intervention notion. If you have a linearly represented concept, this is what these things mean.
Sounds good.
Okay, yeah.
There are a few more questions. Do you want to maybe take them later and continue?
Yeah, let's take them later since I have 15 minutes left, and I'd like to get through, you know, at least a subset of the talk. Okay, so we have some problems still, right? So the first problem is we've now unified unembedding and measurement and embedding and intervention, but we haven't said anything about how the unembedding and embedding representations relate, right? So we still have like two apparently totally distinct notions of linear representation. The other problem, which is not obviously connected, but which turns out to be very closely related, right, is the question of like, well, what, if any, is the right geometric structure to put on the representation space, right? So like, is there a right notion of inner product by which to understand the representations of concepts? Okay, and so maybe plug your ears for the setup bit. I feel like a compulsion to put it in, but maybe I shouldn't. Okay, so just like a little bit of bookkeeping, right? You know, the problem we have right now is that our representations are actually cones, not vectors, because they don't have a notion of magnitude, right? And so just like a little bit of bookkeeping to turn our representations into vectors, right? What we're going to do on the unembedding space is define the space of differences of all unembedding vectors. We're now going to equip that with some inner product. And the thing we're going to be interested in is what's the right inner product to equip it with. And then once we have an inner product, we can get a vector representation of an embedding simply by choosing the element of the cone with norm 1. Okay, so this is just mathematical note keeping, just showing that all of these objects can be well defined. If you're confused by that, please just ignore it. It doesn't really matter that much. Okay, so you might think actually this problem is not a problem at all. There is an obvious inner product to look at a vector space, and that is the Euclidean inner product, right? You know, give you some vectors. You know, in fact, we're so used to Euclidean that people have been using the Euclidean inner product constantly without even thinking about the fact that they're making a choice here, right? But you know, if you do like numpy.cosine, right, you're using Euclidean inner product, you have a vector representation already. You know, why is there a problem here? Like a thing just popped out, let's use that, right? So what's the issue? Well, the observation here is that ultimately we learn the model, so we learn the embedding and unembedding representations in order to get the softmax probabilities right? And the observation here is that there's an non-identifiability in the subjective function, which is if we apply any linear transformation, any invertible linear transformation to the unembedding vectors, right? And then we apply the inverse transpose of that operation to the embedding vectors, then it leaves the softmax probability unchanged, right? And so the point here is that from the perspective of the objective function, right, the embedding vectors are only identified up to invertible linear transformation. And the reason that this is a problem is that inner products are not invariant in general up to invertible linear transformation, right? And so it seems to naturally be the case, right, that the inner product that we learn here, right, is, you know, somehow a function of the random seed, or maybe like, you know, the particular biases of gradient descent or something else, right? There's no reason for it to be semantically meaningful, right? It's like, it's basically arbitrary, right? So Euclidean distance in the representation we happened to learn need not mean anything because it was not even identified, right? This is the problem that we have. Okay, and so what that means in particular is that if we want an inner product that's going to capture semantics, right? So that allows us to like interpret large language models via things like cosine similarity, we need some kind of additional principle for identifying that inner product, right? Like we have to do something extra. Okay, and so the idea that we're going to use in this talk is to define a notion of causal inner product. So we say an inner product is a causal inner product if the representations of every causally separable pair of concepts is orthogonal, right? So the intuition here is that I can freely vary whether the output is in English or in French, or I can vary that freely from whether or not the output is about a man or a woman, right? And so if I can vary these two things freely, right, the sort of natural algebraic structure for encoding that is orthogonality, right? And so we're going to ask for this special kind of structure on our inner product, which is things that are causally separable have orthogonal representations, right? This is the principle. This is the principle that we want to get semantic meaning. Okay, so that's a strong intuition. It turns out that such an inner product has the following very important property, right? Which is that the causal inner product, or any causal inner product rather, unifies the embedding and unembedding representations according to the following map, which says that the embedding representation of a concept W is just the generalized transpose of the unembedding representation, right? So in the naive thing, we have unembeddings are column vectors, we have embeddings are row vectors, right? The sort of most obvious way of like mapping one to the other is to take a transpose. The transpose is not the right thing because that's a Euclidean notion, right? But if we just use the generalized notion corresponding to a more general inner product, that is the right thing, right? So you can think of this as a mapping from column vectors to row vectors. And this is just the Riesz isomorphism, if that is meaningful to you. Right, and so the overall point is that if we look in the default representation space, the space that we happened to have learned, right, you know, just out of like running our LLM, we have for the concept of say male to female, one vector which corresponds to differences of sentences, and a different vector which corresponds to differences of words, right? And this happens for all concepts. Right, but if we now apply a linear transformation such that after linear transformation, the Euclidean inner product is a causal inner product, then in this modified representation, what we will find is that the word and sentence representations of the concept are the same vector, right? So we've unified that vector representation, and additionally, we have orthogonality of all causally separable concepts, right? And it's that orthogonality is the thing that ultimately gives us this unification. Okay, so we've now succeeded at doing that. Okay, so we still have a problem, right? Which is we said, well, what we want is this causal separability property, or what we want is this causal inner product structure, right? But that's ultimately defined that's ultimately defined with respect to like causal quantities, right? And so the issue is, even though we can talk about that mathematically, it's not at all obvious how to construct this, right? So how do we write code about this, right? Okay, so the idea here is this is like a very sort of standard causal flavor of argument, right? What we want is a causal criterion where we can actually measure our statistical independencies, right? And so what we want is some kind of data set where things that are causally separable are statistically independent, right? Because if we have such a structure, then we can use the measurability of the statistical independence in order to identify a causal inner product, right? So this is not exactly a standard causal identification argument, but it's like ultimately the bones are the same, right? Okay, and so the question is, well, what is such a data set, right, where things that are causally separable would also be statistically independent, right? And the assumption that we're going to make is that if I uniformly sample words from the dictionary, right, then concepts that are causally separable as expressed in vocabulary words are also statistically independent, right? And so this is just saying something like, well, it might be the case in natural language that like French writing is more frequently about men than English writing is, right? So if I just looked at like sample passages of Wikipedia text, right, I would not have statistical independence between French and male, right? But the nature of dictionary words is basically just like, well, we have words in English which express exactly the variability in existing concepts, right? And so that sort of minimalism breaks the statistical independencies in natural language and makes it plausible that in fact statistical independency in vocabulary terms will correspond to causal separability. Okay, and the result is if you believe that assumption, which I'm going to push on, but like meditate on it, and you'll see it somewhat reasonable. If you believe that assumption, then we can identify the causal inner product, right, as this thing, which involves the inverse covariance matrix of the word vocabularies. Okay, so I'm just going to fly through the experiments. Okay, so the setup of the experiments, these are all on Llama 2.7b. What we're going to do is look at the representations of 27 concepts defined by counterfactual pairs of words. All of these concepts are from the big analogy test set, plus some on language translation. Okay, the very first question is, are there linear representations of concepts? So do these things actually exist, right? The structure that we look at here is, so here's a concept which is country to capital, right? What we do is look at pairs like Paris, France, Tokyo, Japan, Cairo, Egypt, and so forth, right? And we say, is there a common direction, right, where all such pairs have a large positive inner product with that common direction, right, where large means relative to random pairs, right? And we see that indeed for 26 of the 27 concepts we look at, there's like this structure comes up, right? So there's like a very clear, all of these pairs share a common direction, right? And it's not like literally identical because there's like a little bit of like noise in there, right? But it's like there's very strong evidence that indeed these linear representations exist. Okay, the second question is, do we actually succeed in representing causally separable concepts orthogonally? So here we have the heat map of the absolute value of the cosine inner product, the causal cosine inner product of all of these concepts. What we see is most things are orthogonal. You notice this blockwise structure. The blockwise structure is corresponding to concepts that are not causally separable, right? And if you just meditate on this plot for long enough, you'll see that these things really make sense. So for example, we have English versus French is indeed orthogonal to male versus female. But there's an interesting thing, which is English versus German is not orthogonal to lower versus uppercase. There's a meaningful inner product there. And the reason is there's just different capitalization conventions in English versus German, right? And so what we're seeing is like these actually are semantically related because they cannot be varied freely in an interventional sense, right? Like if you change from English to German, you also change like the capitalization that you will use for the next word. Okay, so the causal inner product makes sense. I'll just mention that these two things are comparisons with like other non-causal inner products, and meditating on these shows that like they make much less sense, right? So indeed, the thing that we identify captures semantics much better than just using the naive Euclidean or using like a random choice of inner product. Okay.
Sorry to interrupt. If you could wrap up in around 4 to 5 minutes, that would be.
Yeah. I'm on track. Cool. I mean, I'm not on track, but I'll just skip the second half of the talk, so it'll be solid. Okay, so another claim was that the unembedding representation, so the thing learned from counterfactual pairs, works as a linear probe on the embeddings produced by the model. Here's an experiment showing this, where we take passages from either English or French Wikipedia, right, and show that the unembedding thing can predict which Wikipedia we took the output from. The final one is this idea that we can modify a concept in isolation by adding on the generalized transpose of the word pair thing, right? So this is like using that Reese representation to get an interventional representation. And what these plots show is basically we take sentences like long live the whatever, and then we add on this male to female direction, right? What happens is the relative probability of queen versus king starts to heavily favor queen, right? Without changing at all the relative probability of capitalized king versus lowercase king, right? So we're modifying this concept in isolation if we change the male to female direction. Similarly, if we change the lowercase to uppercase direction, we modify that concept in isolation without doing anything here. And if we change the French to Spanish direction, we don't change the relative probabilities of like king versus queen or lowercase king to uppercase king at all, right? So key point is French and Spanish have very similar capitalization conventions. So like we have orthogonality there. Okay, so I'm just gonna totally skip this. Actually, I'll maybe mention the question, right? Which is, so this tells you if you have one of these notions of linearity, then you have all of them. We have a unification, but it doesn't tell you anything about where the linearity comes from in the first place, right? Like, why is that structure there? So is it about transformer architectures or stochastic gradient descent or something else? It turns out that you can do a very general notion of this like linear representation thing, yada, yada, yada. Eventually, you can give an extremely general notion of the embedding subspace notion, right, in some very general vector space. And then a result that you get, and I'm sorry, this is not going to make any sense, but I'll just say it anyways. A result that you get is that there's a totally generic representation of probability distributions, which is the Stein score, right? So there's some like functional vector representation notion generically of conditional probability distributions. And that functional notion will always have this arithmetic composability or like generalized subspace embedding notion. So I'll throw this up here. I haven't made this argument, but I just want you to know. It turns out that this like linear structure, right, is ultimately a consequence of the structure of probability theory and is not actually particularly related to the optimization procedure or to like details of the model architecture. Right, so there is a generic representation where you always have this linearity. Okay, and so you can use this to generalize this notion out from language models to like look at diffusion models, and so we can make sense of this idea of like project out attributes like style, right, and change them, right, or project out attributes like sex and change them to a random sample. Right, and so the point is just like here we're showing that we can go from like modifying next words to with this generalized notion of representation, modifying like semantic aspects in diffusion models, which is a very different kind of conditional probability model. Okay, so conclusions. If you get the causal structure right, the notion of linear representation is well defined. The causal language here is actually totally key. Like you could not formulate any results without this like thinking about interventions. The causal inner product gives you a sensible geometry, and in fact, you really need the causal inner product, or the geometry really doesn't totally make sense. And in general, like the origin of this linear structure is about like the structure of probability theory, although I just hand waved that one away, but it is an important result. And so you can see the papers to get these results phrased more precisely, and I encourage you to look at them. Okay, cool. And I'll wrap up there since I'm a little bit over. Thank you.
Thanks, Victor. Sorry for making a wrap up. Looks like we skipped some really interesting results. Okay, great. So we have actually quite a few questions in the Q&A, but just in the interest of time, let's move to the discussion, and then we will have hopefully some time for extra questions. So Francesco, Victor, can you stop sharing your screen? And Francesco, feel free to start. Thank you.
Yes. Can I stop sharing my screen?
It's done.
Okay.
Nice. All right. Great.
Okay, I think you should be able to see my full screen slides. Is that right?
Yes.
Okay, wonderful. So I wanted to start the discussion with a small, like, 2 slides on disentanglement, and also a little bit why people, at least like, used to care about this. And then I want to start a discussion and how we relate this linear representation hypothesis to things that people used to do in disentanglement and perhaps are still doing right now. So in the simplest formulation, when we were talking about disentangled representations, we were assuming that we had access to high-dimensional observations And these were generated by some independent factors variations, which in Victor's languages would be the concepts. And then we want to learn a representation which captures all the semantic information about the scene, so it should be a lossless compression, but also should align the coordinates of the representation into these different concepts. We had these results stating that if you don't make any extra assumptions, but only observe a bunch of independent samples, then you cannot learn a disentangled representation because you don't know essentially which are the right factors variations that you should disentangle. And here is where we started introducing assumptions, which in some sense are similar to directions, except we wanted to enforce that these directions had to be then axis aligned during training. Because when I tell you that these pairs of images are kind of like the start and end point of a small vector that describes a direction, then you can leverage these assumptions for training. And hence also discard which models are incorrect. And with this type of weak supervision, we could actually see a lot of benefits of this entangled representation, which I'm now gonna like just gloss over. We had interesting applications in fairness, in abstract visual reasoning, and strong generalization, which was also like, I guess, relevant for the series. And now going back to the linear representation hypothesis. So the premise to me seems to be that language models learn concepts in linear representations. This whole disentanglement business, which was about aligning this concept with axes during training, is actually unnecessary, because ultimately what we care about is having these inner products. Because if we have these inner products, it means that we can project in these spaces, and then we can do whatever we want, and it doesn't really matter whether the model actually has these concepts aligned with the dimension of the representation. And also in Victor's presentation, he touched on this problem that now we have many possible causal inner products, and we still leverage some sort of assumptions. And with these assumptions, we can get lots of benefits that are also very similar to the ones that we were arguing back then in this entanglement setting. But now the key difference is that these emerge in the model, and we don't need to enforce these globally disentangled representations. So I have a few discussion points, and I can just leave the slide here. And Victor, you can choose what do you want to answer first or in which order. But I just want to explain them quickly, and then I can give you back the stage. So it seems to me that you are arguing that we should move the problem from learning disentangled representations to finding them. You call them concept spaces, but to me they're very similar. And so I was wondering if you could elaborate a little bit on what are the advantages of doing so beyond it already seems to work. And another interesting aspect, which is maybe a corollary of the first question, is more recently now, like in as disentanglement morphed into having latent variables that depend on each other, and what can you say about those? And so I'm wondering whether there is also a generalization of your hypothesis in this setting where now you have multiple concepts that could be dependent on each other. And then the third question I had was about how do we assign meaning to these concepts? Because if I define meaning as an equivalence class, which is defined by a discriminant, and here I'm using the notation from this paper, which I think is very interesting, Taming AI bots, then the implication is that the meaning is attributed to the data, is not natively present in the data. But you seem to associate some meaning to these concepts. And so the question becomes then, how do we ground it? So are there many concepts, but only some of them have meanings? Or do we assign meaning to concepts by constructing them, for example, like building these pairs, like the vector that represent the difference between men and women, and so on. And maybe the fourth question is maybe less interesting, since you kind of like skip that part. This linearity of independent variables also comes out in some of our work of causal discovery. So I was wondering whether you actually thought there was some deeper connection or not. And with this, I give you back the stage.
Cool. Okay, so I think I have 2 minutes. Let me try and answer the third question, which I think is like the conceptual one, or like everything else sort of flows from that. So I think there's like sort of 2 possible views about semantic structure in these models. So one view, which is actually like in the process of making a comeback, and which I associate with disentangled representation learning, is that there exists some set of discrete concepts that like were really there in the data generating process, right? So these are things like, what language is the output in, and like, I don't know, what is the grammar and whatever else, right? Like it's maybe very large, right? But there's some like explicated set, discrete set. And if I just knew all of those things, I would know everything that was in the structure of the data, right? The other view, which is a bit more nuanced to say, is that there isn't really like a fundamental discretization of meaning, right? Instead, what we have actually are like particular points within a space that's fundamentally a continuous space, right? And so, like maybe a sharp version of that, right, is we have a concept which is English versus German, and a concept which is uppercase versus lowercase, right? And it's not clear like how to make sense of the idea of these as like distinct concepts, right? Like it's not obvious to me what kind of discretization, or if there is a fundamental discretization which takes these 2 things to really be like different points, right? I mean, there may be, I'm not ideologically against it, but the point is like, because these things co-vary, right? They're like related to each other, and they're related to each other in a particular way, right? Which you sort of hope that the geometry of the representation captures, right? But like I could imagine having like, one fixed underlying geometric structure, right, which is captured semantics, and then many distinct possible high dimensional discrete structures, which equally well explain the variability, say across sentences in the observed geometry, right? And so I guess like my feeling overall is like, or my intuition is that the right way of understanding semantics is in this continuous view, right? And so that's what I see as like the fundamental distinction versus like this disentanglement literature. But I will say like I think a major weakness of this, right, is that right now it feels like in order to monitor a concept, I have to define a priori what that concept is, right? And like construct it and label it and look for it, right? Whereas the thing that would be much more powerful, and there are hints that you can actually do in language models, are using things like sparsity or whatever to just like automatically subdivide variation in the data into interpretable concepts, right? And because you might actually want to monitor like many millions of interpretable concepts, some kind of automation and like these ideas from disentanglement, I think, will be very, very important. And I think like the thing that remains is sort of like figuring out how to reconcile these 2 things, right? So like using like disentanglement type ideas to like automatically identify concepts that you look at, but still keeping enough of the continuous structure that you're able to like exploit things like geometry on the underlying space for interpretability and control. Okay, so we're over time for sure. So maybe I'll just dodge your other questions. I think like that's my answer for like 1 through 3 in aggregate, which is, I think both things are important, and I think the task is unify these views.
Yeah, exactly. I maybe wanted to conclude that I really like your perspective, and also how actually maybe there is a path to go beyond I guess that's what I wanted to write here in the slide, these independently controllable concepts, and that's very exciting like research area, and I would add that it's also extremely important in my opinion, so I'm really looking forward to see what comes next.
Yeah, for sure. Strongly agree with that. Cool. I don't know if we have a hard stop. I'm happy to stick around for a bit to answer the remaining Q&A. I don't know.
Yeah, so there is, okay, so one thing is that we do have a lot of questions in the Q&A. So I just want to say, if we don't get to any questions live, they will all be forwarded to Victor. So if you want to follow up with him by email, that's totally welcome. I think there is at least one question that I think Sarah flagged as something that we might want to ask. So Sarah, if you want to.
Yeah, I think there was a question from Yanai Elazar. And the question was about expanding on the importance of the location in the network where such linear concepts reside. And then the question was an intervention or of the presence of linear concepts in the last layer. So before the last matrix multiplication or softmax operation may have different implications than its presence in the earlier layers.
Yeah, okay. So that's a great point, and is like genuinely a weakness of like or not our understanding, at least my understanding at this point, right? So the way that we're abstracting the language model is completely agnostic to the particular structure of the neural network, right? So from our perspective, the embedding representation is actually just the contextualized token at the language model output. Right. And so, of course, I'm sure you're familiar. There's like a large body of work trying to like isolate meaning in language models, like looking at where to do interventions and so forth. This is also very empirical. And it's not yet clear exactly how the results here connect with those results. So some things are clear, right? So in particular, like these three notions of representation, that still comes up, like that's fundamental. We will always have this primal and dual space vector structure, even at the intermediate layers. Unfortunately, it's really not clear how to identify a causal inner product in the intermediate layers right now. So that's like an active problem, which I have to admit I'm a bit stuck on. But like at least the problem is there, so hopefully like somebody clever solves it. Beyond that, I am actually not even so convinced at the moment that like localization as a program completely makes sense. I'm kind of like agnostic to that. There are also results sort of pushing back on this, like say the places that you find, the locations that you find with like Rome or whatever are actually not optimal places to intervene on the representation in order to change outputs. So there's some like weird contradictions there. Generally, I guess like, another major open problem is just pushing these results through to the internal layers, which should hopefully clean up a lot of the mechanistic interpretability of the internal layers. But yeah, open problem.
All right, great. Thank you so much, Victor. And Francesco. All right, let me share my screen so we can wrap up. Wonderful. All right. So once again, thanks to Victor and Francesco for nice talks. I'm sorry we didn't get to answer all the questions. There have been so many questions. I think people are really interested in this topic, and hopefully you can all look through the slides and send any follow-up questions to Victor or Francesco if you have them. All right, next week we'll have a talk from Sarah Robertson from Harvard. This will be the last talk in our thematic series for this January. So hopefully we see you all there, and have a great rest of your week. Thank you. I don't know how to